Second part of Chapter 9, Apes, is going to start talking about different population patterns. So if we look at the first one, which is A, the red one, rather stable, not a lot of fluctuations, maybe a little up and down, that's about it. B is eruptive. That's characteristic of like mosquitoes in Wisconsin, where the weather is perfect for them. Warm and lots of rain, boom, their population shoots up. C, cyclical, up and down, very typical pattern for predator-prey relationships. And D, which is the very top one, is very irregular, no rhyme or reason. So kind of just a little overview. Stable is going to slightly go above and beyond carrying capacity. Eruptive, like mosquitoes, explodes to a high level when favorable conditions. Cyclical, just normal predator-prey relationships, and irregular, of course, no. All predator-prey relationship, you can see the mighty moose and the wolf. The wolf eats the moose. As the wolf population goes up, which we can see right here, what's naturally going to happen is the moose population is going to go down because we have lots of wolves eating lots of moose, and vice versa. What happens then is when we run out of food, the wolf population goes down and the moose population is going to rebound. So pretty much a cyclical kind of pattern. Species do have different reproductive patterns. These are very, very important. R-selected versus K-selected species. R-selected species are also known as opportunists. They take opportunity when they can with favorable conditions. So, being opportunistic, they have very high rates of reproduction. Most of these are going to be things like mosquitoes, like insects. Again, they need, they're opportunists. They need to take advantage of situations like weather, like moisture. These creatures spend most of their time with their rate of reproduction. If you think about a fly, for example, a fly lives maybe 3-4 days, a week or two, and most of their life is doing a little eating and getting ready to reproduce. Very little parental care. They lay their thousands of eggs and they're gone. Many small offspring, fish are another example of this, reproduce when conditions are favorable, go through irregular population cycles, again, because they have to wait for those favorable times. Examples are algae, bacteria, rodents like mice, annual plants, insects are examples. The opposite of this is K-selected species, competitors. We are in this classification. We tend to reproduce later in life. Small number of offspring, maybe generally one, if not maybe two, maybe three at a time. That's it. Not thousands like the mosquitoes or flies. Another characteristic of K-selected species is we're born fairly large. Most of you are born 7-8 pounds or so, and obviously quite different from little insects. We are cared for and protected by parents, so our parents obviously nurse us and help us all the way through age 18, if not beyond, so there's much more parental care. We mature much more slowly than many species, follow a logistic growth curve, so we tend to kind of go up and down in our patterns. We're very prone to extinction too because we don't lay a lot of offspring and we don't have nearly the genetic diversity of something like bacteria or insects. And we need a suitable habitat to live. This is what's called a survival curve. There's 3 ways of looking at survival curves. On the very top, we've got a species kind of like we would fit into. 100% of our persons surviving is right up here, or creatures. We generally don't start dying till later in life, and that's a characteristic of a K-selected species. Whereas R-selected species, one of the reasons they have so many offspring is so many die right away. So this is an early loss. If you take a look at this, a lot of them die right away. Think about sea turtles too. But maybe if 100 of them are, the eggs are laid and hatched, maybe 1 or 2 will actually make it to the ocean and reach maturity because of so much competition. And then there's things like birds, which just for no rhyme or reason, some die early, some die middle, some die late. Really no do that. So late loss, early loss, and constant loss. A life table shows the number of individuals at each age on a survivalship curve. Who really cares about this are things like insurance companies, and they get into what's called risk management. So if you're born, unfortunately, with poverty, if you tend to drive a long distance, your likelihood of surviving is decreased, and there's other variables with that too. The effects of genetic variations on population size, this goes back to the old biology days. Genetic diversity is very important for a species to survive, of course. We have something called the founder effect. That's when few individuals move to a new location and are isolated from the original population. They tend to have what's called a limited genetic diversity or a limited gene pool. Very good example of this is like the Amish people who came from Europe at one time, came to the United States. Very small populations, isolated populations tend to marry within those populations. Their genetic diversity is not real deep that another person's would be, that somebody came from like Asia, for example, and married somebody from the United States. Much deeper gene pool. You can see something called polydacty, which is a genetic trait that actually keeps popping up in people because of a lack of variance. Demographic bottleneck is when few individuals survive a catastrophe. So let's say there's a population, the white-tailed deer in Wisconsin, 500,000. We have a hemorrhagic fever go through, and what happens is it kills 100,000 of the 500,000. Boom, genetic diversity cut down. Genetic drift, random changes in gene frequencies. Some may breed more than others. That may help or hurt survival of a population. Genetic drift is kind of the idea, again, in Wisconsin with our white-tailed deer population. The deer that are the strongest, that have the antlers that they can use to fight off and overall are the healthiest, they're the ones that tend to reproduce. Not only do they mate with one or female, but they may mate with multiple. Inbreeding bad, that's when members of a small population exchange genes. That's the idea of having offspring. That's why you have to marry outside your second cousin, I believe it is, because otherwise your first cousin and your brothers and sisters have genetic close to yours. The reality is we've altered about 83% of our Earth's land surface since we got here, or since we've grown exponentially. We've destructed, we've fragmented. Fragmenting, by the way, is partially destroying a forest, which is really bad too, just like a total clear cut, for example. We've degraded wildlife habitats. That's the #1 reason species die out. We've reduced biodiversity. Of course, we clear land, we do monoculture. We've reduced species and interactions. Opportunistic species are costly to control, which was talked about during our pesticide unit. And pathogenic species are a real concern. It's really, what's probably going to wipe the human population out is this tiny little bacteria, the tiny little virus. That's what's going to get us. We're not exempt from nature's population control at all. As I said, there's a blight fungus that went through Ireland back in 1845 when we had the potato crop damaged beyond what they could support, so their carrying capacity was pretty much wiped out, so they came to the United States. Bubonic plague in the 14th century in Europe wiped out a lot of people too, small little bacteria. And the AIDS virus, of course, which is a concern particularly in developing nations like Africa. In that continent, that's a global epidemic, but it's really hitting the continent bad. A little case study with our exploding white-tailed deer to end this in the United States. In 1900, we've destroyed a lot of deer habitat. We're building houses, we're cutting down forests where they like to live, and we had uncontrolled hunting. So what happened is the deer population in the early 1900s just devastated. Then what happened in the 1920s and 1930s, we started recognizing this and got laws in order to protect the deer. Now, because we have a high deer population, they're getting hit by things like Lyme's disease, which is carried by a tick. Obviously, the more deer population, even around Brookfield here, we get more deer accidents. They eat our garden plants and shrubs, which we don't like. So how do we control the deer population? Well, the way it's managed in Wisconsin, of course, is they estimate the deer population and then give out X number of deer permits to shoot those deer to try to keep their numbers within reason. All right, that's it for Chapter 9.